Hi everyone, so in this video we are going to discuss on tutorial 15. The topic is energy of a satellite and escape velocity. Okay, so we read the question. The moon takes 27 days to go around the earth in an orbit of radius 3.8 times 10 to the power of 8 meter. So the mass of the earth is 6 times 10 to the power of 24 kilogram, and that of the moon is 7.4 times 10 to the power of 22 kilogram. So calculate the gravitational potential energy, the kinetic energy, and the total energy of the moon in its orbit. Okay, so we are given period. Okay, 27 days is the period, and the distance to 3.8 times 10 to the power of 8 meter. Okay, so the mass of the earth 6 times 10 to the power of 24 kilogram, and the mass of the moon is 7.4 times 10 to the power of 22 kilogram. Okay, we're going to find gravitational potential energy, which is symbol used U. Okay, the formula is negative GMM over R. So we substitute all the values: gravitational constant, mass of the Earth, and mass of the moon. Okay, divided by distance between them. Okay, so the answer is negative 7.79 times 10 to the power of 28 joule. Okay, next we are going to solve for question 1b, the kinetic energy, symbol K. So the kinetic energy, we can use formula GMM over 2R. Okay, positive, you must put negative in the formula, but kinetic energy of the satellite, no need to put the negative. Okay, we approve this equation, okay, the formula in our lesson. Okay, so now we straight away use the formula. So substitute all the values into the equation, and we get 3.90 times 10 to the power of 28 joule. Okay, next, the total of energy. So the total energy symbol used is E. Okay, so the formula for total energy is negative GMM over 2R. So the formula for E is same as K, except that it has negative in front. Yeah? Okay, so we substitute all the values, and the answer is negative 3.90 times 10 to the power of 28 joule. Okay, so be careful with the formula used in this question. Okay, next we go to question 2. The figure below shows the elliptical orbit of a planet round the sun. Okay, so mark on the figure the point X where the speed of the planet is greatest, and the point Y where the speed of the planet is the smallest. Okay, so the speed of the planet greatest, okay, where is it? So from the formula, kinetic energy equals to GMM over 2R. Okay, so the the question asks for the greatest speed, so that's mean the kinetic energy is the largest. So when we increase the kinetic energy, so the distance will be smaller. Okay, so that's mean where is it? Should be this point. This point. So the distance of the planet from the sun is smallest here. So therefore, the kinetic energy will be greatest at this point. Okay, next is the point Y. Okay, point Y is where the speed of the planet is smallest. So it will be opposite side, because if the distance, if the kinetic energy, if the speed smallest, so that's mean the kinetic energy decrease, so the distance will be increased. So that's mean the greatest will be here. Will be here. So you draw the line joining the sun and the planet. Okay, straight line here. Actually, this is the diameter of the shape of the ellipse orbit here. So must draw these two lines joining together to show that this is the smallest distance, and this is the largest distance for the path of the planet around the sun. Okay, so now we go to question 3. the orbits of the Earth and Venus are essentially circular. So if the radius of Venus orbit is 0.723 times the radius of the Earth orbit, so calculate the period of orbit of Venus round the Sun. Okay, so to imagine this, so this is the diagram drawn. So this is the Sun, this is the Venus, and this is the Earth. So the Venus, the radius is given 0.723 r. So times r, the radius of the Earth. Okay, so we are going to calculate the period of orbit of Venus around the Sun. Okay, so we use, because of this is a circular path, so you can use centripetal force, mr omega squared, and this is provided by the force, gravitational force, which is gmm over r squared. So gravitational force provide the centripetal force. Okay, so the omega is angular frequency will be 2 pi over t, and we cross multiply. Okay, so 2 pi here, it becomes 4 pi squared, because square here, and then we cross multiply. So r cubed times r is r squared times r is r cubed over t squared. Okay, so now we have two equations. The first one is for the Earth and Sun. So for the Earth and Sun, gm over 4 pi squared is a constant. So r cubed, okay, this distance Earth to Sun divided by the period Earth traveling the Sun here, 1 year, in 1 year. So we use year, okay, year as a unit. So this is equation 1. And then for equation 2, is this gm over 4 pi squared is a constant. Okay, this for Venus, the distance is 0.723 r. Okay, bracket cube, because the equation here r cube, and then divided by the period that we are going to find. So this is the period of the Venus that we are going to find. So this is equation 2. Okay, then we use a ratio method. Okay, 2 over 1, equation 2 over equation 1. So actually this constant we can cancel out, and we use the ratio method here. Okay, then we find t equals to 0.615 years. Okay, t, the answer is t, period of the Venus is 0.615 years, because just now we use year unit for the period. Okay, so next we go to question 4. Okay, so this is another method. You can use variation method, because we know that gm over 4 pi squared is a constant. So you can put use a variation where r Earth cube over t for Earth squared equals to r for Venus cube over t for Venus squared. Okay, so you can use this method also instead of the ratio method. Actually, both are the same. Both method can be used in the exam. Okay, now we go to question 4. So the table below shows the values for radius r and mass m of the Sun, Earth, and Moon. Okay, the escape velocity from the Earth is 11 km per second. So estimate the escape velocity from the Sun and from the Moon. Okay, so you are given all the values here in the table. So we are going to make use all the values given here. So the solution, we use principle of conservation of energy. Okay, the change in kinetic energy. So we use half mv squared equals to change in potential energy. So the potential energy is gmm over r. So we get V equals to square root of 2 gm over r. Okay, next we substitute the value of escape velocity. This is escape velocity. So remember that the escape velocity, we used the derivation, the principle of conservation of energy. The physics concept we use here is principle of conservation of energy, because the questions want escape velocity. Okay, so V is 11. Square root of 2g. Okay, refer to this formula. So the mass for the Earth, 6 times 10 to the power of 24 over radius of the Earth, 6.4 times 10 to the power of 6. Okay, this is equation 1. For the equation 2, for the sun, so Vs is square root of 2g, so mass of the sun is 2 times 10 to the power of 30 over 7 times 10 to the power of 8. So this is equation 2. So from for the escape velocity of the moon, so equals to square root of 2g, and the mass of the moon, 7.4 times 10 to the power of 22 divided by distance, 1.7 times 10 to the power of 6. Actually, this one radius of the moon. Okay, so this is equation 3. So we have 3 equations by using the values given in the table. Okay, so we are going to find escape velocity from the sun and from the moon. So for the sun, we use equation 1 and equation 2, okay, for the sun. So we use ratio, and for B moon, we use equation 1 over equation 3. Okay, so now we do this. Okay, so I didn't solve final, but you use ratio method, you can find out by yourself. So the Vs, escape velocity for the sun, and escape velocity of the moon by using ratio method. Okay, similar to the methods in question 3. Okay, so next we go to question 5. Okay, question 5. Derive a formula for the escape velocity from the Earth in terms of its diameter d and g, the acceleration due to gravity. Okay, so imagine this is Earth. Okay, on the surface, the object is on the surface. So when the object start to manage to escape from the gravitational pull of the Earth, so we assume at somewhere here, so we can use principle of conservation of energy, where the change in kinetic energy equals to change in potential energy. So, or you can also change in kinetic energy is the loss in kinetic energy, and the change in potential energy will be the gain in potential energy. Okay, so the loss in kinetic energy is half mv. So the v here is the escape velocity that we are going to find. Okay, so the object here will be launched with velocity, escape velocity equals to escape velocity, so that it managed to be at the somewhere here. It can manage to release itself from the gravitational pull of the Earth, right? Okay, so now the gain in potential energy. So when the object is at somewhere here, where it managed to free itself from the gravitational pull, so the gravitational pull, the gravitational potential energy there will be 0. So 0 minus the U or gravitational potential energy at the surface will be gmm over r. So to use gravitational potential energy formula, you must put or bring along together the negative sign. Okay, so that's how we get loss in kinetic energy equals to gain in potential energy. Okay, so now we solve the escape velocity. So this is to illustrate what happened. Okay, kinetic energy, and then gravitational potential energy at initial and at final. Okay. So now we solve for escape velocity, which is equals to square root of 2gm over r. But the questions wants in terms of d, g, and in terms of d and g. So we need to substitute replace the gm here. So we use at the surface, where at the surface of the Earth, the gravitational force, which is equals to mg, equals to gmm over r squared. So this is special case on the surface. Okay, mg equals to gmm over r squared. So this r is radius of the Earth because on the surface. So we can cross multiply, cancel m, M is mass of the object here, so gr squared equals to gm, and we can substitute the gm here with gr squared. Okay, so we substitute there and we get 2gr. Okay, so the diameter is equals to the 2r, right? So the diameter of the earth is equals to 2r, so this 2r we can substitute with d. So because the questions wants in terms of d, so we replace the 2r or substitute the 2r with d. So that's the answer. Okay, so we the question 5, escape velocity in terms of g and d is given by escape velocity equals to square root of gd. Okay, so for the conclusion for this tutorial, be careful with the velocity of the satellite and escape velocity. So for the escape velocity, we use the physics concept we use is a principle of conservation of energy. So when we derive this formula, okay, we get escape velocity equals to square root of 2gr. And be careful with the velocity of the satellite. So velocity of the satellite, we use the centripetal force concept, where is provided by the gravitational force. So let's say the centripetal force is mv squared over r, and the gravitational force gmm over r squared. So we solve for v, we get square root of gr squared over r, right? Or gr squared we can substitute with gm, so we get gm over r. So be careful with the two different velocity. One is escape velocity and the other one is velocity of the satellite. Okay, make sure you don't get confused with the formula used for this escape velocity and velocity of the satellite. Okay, so that's all for the tutorial 15, and bye bye.